Hi, fellow geochemists and geochemistry enthusiasts. Welcome to GeOCHemISTea, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire future geochemists and to introduce our listeners to niche geochemistry topics. I'm your host, Sam Scher, and this month we're talking with Brittany Hupp about probing paleorecords to understand future climates. Brittany Hupp is an assistant professor at George Mason University in the Department of Atmospheric, Oceanic, and Earth Sciences. Brittany, welcome to GeoChemISTea.
Glad to be here. Excited to chat.
Me too. So Brittany specializes in micropaleontology, sedimentology, and low-temperature geochemistry. Her research focuses on reconstructing past climates, ocean conditions, and their influence on marine ecosystems. Through her work, she bridges Earth's history with modern environmental challenges. And this is really just a snapshot of your research. Could you share more about how you got started in geoscience and what led you to this fascinating and specialized field? Also, for our listeners that are interested in the intersection of multiple fields with geochemistry, could you share any advice or insights to help guide their paths?
Yeah, this is a great question to get us started. Let's see. How did I get started in geosciences? I think, like many geoscientists, they probably went to undergrad in pre-med and then discovered that geology is a thing.
I started in biology, so
Right.
different, but yeah. Okay, cool.
Yeah. Yeah. I'll say I grew up in very rural Ohio on a dairy farm. And so in reality, the careers that were available, I like to say, are kind of like the careers on preschool flashcards. So you can be a doctor or a teacher or a nurse or a firefighter or a policeman, right? So of those, I picked doctor and obviously didn't end up going in the medical doctor direction. But I also really liked being outside. Like I said, I grew up on a farm and was outside quite a bit, loved to go hiking and everything. And I really liked science. Yeah. And so I went to undergrad to do pre-med, liked the classes because I liked lots of different types of science, but ultimately was not too excited about going directly in the medical route. I really liked chemistry and I really liked geology. So I decided I'm either going to be a chem major or a geo major. I actually thought I was going to be a pharmacist there for a while. And so I got a job at a pharmacy. And without hopefully insulting too many people, it was the worst job I've ever had in my entire life. And prior to that, I actually worked at a water park. So the relative cleaning up children's vomit versus working in a pharmacy, I was like, I'll go back to the water park. Anywho, focusing back, I liked my geo classes. I decided to go in the geology direction. When I was an undergrad, I was lucky enough to do undergraduate research that was focused on microfossils and doing biostratigraphy. I ultimately went on to do a master's that ended up being much more focused in unconventional reservoirs, doing kind of shale geochemistry. And while I was a master's student, I discovered, well, that I really like geochemistry, not surprisingly, but also that you can actually look at the geochemistry of fossils to learn a lot of things, right? And so I knew that's what I ultimately wanted to do for my PhD. And I was lucky enough to have someone who was willing to take in someone from shale geochemistry to instead do fossil geochemistry for paleoclimate, paleoceanographic reconstructions. And even from that, my whole PhD was focused on using microfossils, both in terms of their paleoecology and their geochemistry, to look at ancient global warming events, which we'll talk about more. But even beyond my PhD, I ended up doing a postdoc actually studying these same organisms in the modern ocean. So I feel like I don't know how this happened, going from somewhere that's very far away from any ocean to now doing seagoing research. Somehow that happened along this trajectory of so many years. Right.
Yeah, even coming from, I grew up on Long Island in New York, which is surrounded by water, had been out on ocean going vessels before. doctor, lawyer, teacher, business were the fields that were open to me as well. So I think it's something about living, I don't even know if it's like east of the Mississippi in the United States, which is a river to people that don't know that cuts the entire US in kind of half or what, but it just seems to be something that's the only thing offered. And so if I could put in a plug for college, that's something that kind of opened the gates for me for the geosciences too. I had never heard of it. I took an earth science class, but that was just a throwaway that you had to take in high school. It was just like the ninth grade course, the quote, easiest course that you could take. And you just had to do it so that you could move on to get into the real pure sciences, if you will. And now I just see how wrong all that is. Yeah, same. I didn't grow up on a dairy farm, but
Long Island, I'm sure it's just the same, right?
the same as Ohio, yeah. I've been
Yeah.
to Ohio. I'm gonna go with it's not. It's not any better necessarily, but I
My
love talking to people from the Midwest. It's just so outrageous to me growing up on a farm. It just blows my mind. How big the farm was, like, really big?
We had it wasn't that big. We had maybe 200 head of cattle
That's
at
a lot of
our
cattle.
max. Yeah. Yeah. It is a lot when you're like on a dairy farm, you have to milk them multiple times a day. So
Wow.
it is a lot for a small team of people. Yeah. It is crazy. Even going back, my brother is still a farmer. So going back to my childhood home, very different than
Yeah.
pretty much everything since then. So yeah, it's been an interesting ride for sure.
Getting back to it though. So, any advice that you would give to people that are interested in pursuing some kind of route like yours, which is just really just a blend of disciplines that are all extremely different and interesting? What can you say?
Yeah, yeah. I would definitely say don't be afraid to take that kind of one step to the left, right? One step out of your kind of comfort zone or box, because even if you shift research directions, there's a high likelihood that you have some sort of applicable skill. And also in all of these things, like tackling interdisciplinary research, slightly shifting research gears along your trajectory really just requires you to be coachable and self motivated. Are you open to learning new things? And are you open to also reaching out to the contacts and the people you need to help develop those skill sets, right? So, if you're interested in something, I'd say go for it. I was really worried, especially going from master's to PhD. When you're doing undergrad, there's only so many things that you're exposed to, right?
Mm.
You only take so many classes and they're taught at a certain level. I went to an undergrad where we didn't have a graduate program, right? So I didn't necessarily have that direct example of what graduate research looks like. And so even going to grad school, I was just exposed to so many more research fields, right? And so I think it's important, I don't know, that you're willing to like chase what you're interested in and advocate for yourself. And don't be afraid to really focus on expanding your network in that direction, right? Because there's a lot of people who are interested in helping early career folks learn more about the subject that they love. I don't know. So I guess that's what I'd say. Don't be afraid. I know a lot of folks who, especially in the graduate school levels, right, will do their master's and think they can't pivot at all for a PhD, or even do an undergrad research in something and pivot to something totally different for grad school. And that's just not the case. They really can, especially if they're open and willing to learn and motivated.
I think
Yeah.
that's such a great point. Yeah, and I would say too, even though I went to a school that was really big in graduate studies, I had just a desire to do research, so I knew what I was getting into, but it didn't change the fact that the professor that I selected to work with, and I didn't quite know this or appreciate it at the time, but his style was to throw you in the deep end, sink or float, right? And so you just got to recognize that there may be some professors that are more hand holding, but it's not the job of the graduate professor to hold your hand through the whole thing. And so it's just something to be ready for. And it's not just because you see other people succeeding, it doesn't mean that it's easy. And it's something to appreciate too.
My gosh, that's definitely it. Just because you see other people succeeding does not mean that it's easy, right? Just really pushing yourself because, like you said, there's a high probability that you might get an advisor that is not going to sit there and walk you through it. So really being able to self-motivate and reach out to people who can help you. I would say even now it's very interesting because now I have my like first swath of graduate students,
Mm.
and it's an interesting kind of flipping the script there at this point as like an earlier career scientist. And I'm always really impressed when my students can go out of their way to seek out external collaborators that can help them solve a problem. So,
Yeah, and that's something that I had to do quite a bit, and that was what was really cool about my department. It was just so big with both a lot of graduate students, but also a lot of not necessarily other professors, which is true, but there was a lot of, like, research associates as well, and so just being able to seek out people that you knew could help you with a specific problem that you had, and just not being afraid to ask questions. Nobody's gonna do your work for you, but at the same time, being open to just of course, you're not gonna know everything, that's just crazy. You can't know everything because that's why you're there, to learn.
yeah, yeah.
No, that's really cool, such a great points. Thank you. So let's flip this now. I loved all this. This is really good points, and I hope people were able to take something away from it. But now it's tea time. So I want everybody to grab their cups because it's time to spill. What do you got?
My gosh. Okay. Yes. So for this tea time, I have a funny story or at least an interesting experience. I'm sure we'll talk more about my research, but one big component of my more recent research has involved going on research cruises. So something where you get on a boat and you leave the port and you might be on that boat for 2, 3 weeks. I have a lot of colleagues that end up going on cruises that are multiple months, right? But once you set sail, you're stuck with your group of people for however long it's going to be, right? And so let's see here. A couple years ago, I was on a cruise. It was set to be 2 weeks. And so we left, let's see here. I think we left from San Francisco for that one. We were going to be traveling throughout the Northern California Current, which is off the west coast of the US, right? Throughout that area. And we set off. We made it about 2 days of sampling, doing the work we were planning to do when we started having a problem with one of our engines. And so ultimately, what ended up happening is we had to quit doing all of our science. And then we just had to transit very slowly all the way from, again, this is offshore Northern California, all the way up to Seattle. So it was about 10 days of sitting on a boat with, I don't even know if there were 40 people on it, 30 people maybe, doing nothing because there's really not much. We could not do any type of sampling, no deploying of instruments. And so this creates a very interesting kind of like social situation that you're in on this boat just for to paint the picture, right? We have multiple labs, but really you just have your bunk room, which is shared with 2 to 3 other people. And there's a dining area. And then there's one room with one big screen TV and 200 movies, right? And so that's essentially what we have for 10 days is just each other and that. And sometimes we do get downtime if we have long transit. So I had brought a card game called Coup. Maybe some of your listeners have played this before, but for context, it's something where it's a very simple card game, but you're like lying about your identity to get forward, to earn more money, like within this game, right? Anywho, so I was like, okay, I have this game. It's short. It's like easy to play. And so I teach many people who are on the boat to do it, including some fellow scientists and the chief scientists. And let's just say we were about 3 rounds in before one of the chief scientists and one of the other scientists were yelling at each other and crying. So it got really intense. I was excited to play this, which is super fun, but I had no idea that it was going to actually like rip the fabric of our serenity. And these people didn't talk to each other for 24 hours. So it was a lot for being just on a boat, thinking I had a really great idea of a game we could play. Yeah. So I will
What were
say
the
a lot.
lies told?
What were the lies? So it's something where like, you have two different types of people. There's several different types of people. You're trying to be two of them, and you can lie to get ahead in the game. And one person was saying, oh, you lied, but didn't admit you were lying when you were supposed to, so you shouldn't have gotten. Either way, it wasn't important. It was not important.
Oh my God.
But there were a lot of high emotions, that's for sure. And I really was just excited to play this game. So, word to the wise, if you're trapped anywhere with people for long periods of time and can't go anywhere, yeah, don't play that game. I'll also say, sorry, you go.
No, I was just thinking to myself that, I don't know, is everybody just afraid that they're just going to be lost at sea for life? Was it just like a slower engine getting you home? Or, yeah, okay. So we're just going, instead of 15 knots, we're going like 3.
Pretty
Yeah.
much.
And up and down seas, like in a Viking, just not pretty. Okay.
Yeah, luckily the seas weren't too bad. We
Okay.
have had some very crazy moments in terms of just really big waves, like inundating the decks when you're out there and stuff, which is also crazy in its own way. Yes, but I'll say one other component to this, which sounds absurd, but again, remember, we're on this boat 10 days. Like, you can't call people, by the way. You can't stream anything. You can't watch YouTube. You can't FaceTime. Just there. There was like a very strict mealtime schedule. And so every time it was time for dinner, we'd all like shuffle into the eating area and we would call it trough time because we felt like cattle going to the trough because that's the only thing that adds like stability to these long days of just doing nothing.
Oh my God.
Yeah. It was a crazy time.
I'm not like afraid of the water, but this whole thing just sounds horrific to me. It sounds like, I don't know. Yeah. I'm thinking of like the Poseidon Adventure, which is just this truly awful movie. I watched the original one because they remade it with Fergie in the 2000s, which is not relevant to the story.
It's a choice, though.
It's a choice. My brother loved boats growing up, and it's just a story about how this cruise liner, there's like a rogue wave at sea and it just capsizes and everybody's trying to live or die or whatever. Anyway, this whole thing sounds horrific. This is what it reminds me of.
Thankfully, this is more chill than that. I think it's just trying not to get on each
slow
other's
engine.
nerves.
Yeah, and you did with the coup game.
Gosh.
Yeah.
Also, a great game. Would plug it. And in normal circumstances, I think it would go over pretty well.
Okay. Oh,
Yeah.
boy. Okay. I like that. Oh my God. I've had people that have done cruises for volcanology, kind of C4 spreading and that kind of thing, but I don't know, it just never really sounded something like that I would want to do necessarily. So it's cool when I talk to other people that do it for science. I love it, but it's just, I don't know. I'm just much happier just drilling on land.
Yeah. I will say we were in like a super beautiful area that has a lot of whales. And so we would see whale sightings like all the time. Actually, some folks who were on the cruise, that was like what they were doing was logging and identifying different whales that were there. Yeah. So that was one plus. I'll also say one person on the cruise really loves Twilight and they had all the Twilight movies. And so we ended up watching all of them, which I have not seen in many years. So that was interesting. We also watched all the Da Vinci codes. So this tells you if you're stuck on this like desert island, the things that you could do with these limited resources.
Below deck, but science version. I love it. Okay.
Oh my gosh. See, I didn't even know about that show till afterwards, and I think about it all the time. Yeah.
Oh my God. All right. So look, guys, Brittany and we're part of the Geological Society of Washington, D.C. And that's when I first met her. And I heard her talk about her research. And this was only a few months ago. And I thought it was just so fascinating and such an interesting interplay between a lot of different sciences and geochemistry. And that's when I was like, we have to have her talk on the show. So for this episode, because I know absolutely nothing about what Brittany does other than what I saw in her talk, which she also won an award for, which was really cool. Yeah, no big deal. Best talk of the year. She's flipping her hair. Yeah, so she sent me 4 papers, which I really appreciated because I'm definitely very underread about the carbon cycle, climate, and the biosphere. I have all the links on our website and in the show notes for you guys to take a look at as well. So, Brittany, could you did a little bit in your intro, but could you first set us up and explain your research so that we could transition really cleanly into the Q&A, everybody here being a little bit more informed?
Yeah, definitely. I would say the bulk of my research falls under kind of two categories. So, one, I'm really interested in investigating past abrupt climate change events, right? So, we're going to talk more about this, but a lot of my research has been focused on the Paleocene-Eocene Thermal Maximum, or the PETM, which is a really great ancient analog for thinking about essentially the future consequences of modern climate change, right? And so I do a lot of work using microfossils, investigating their ecology and their geochemistry, while also thinking about the sedimentology to reconstruct oceanographic and ecological changes during past abrupt climate change events. So that's one half of it. In addition to that, a lot of the work that I do looking at paleorecords uses what are known as foraminifera. I know a lot of geoscientists have probably at least heard of foraminifera before, but we'll chat about those more. But these critters have been around for a super long time. They have a really robust fossil record, and there's so many different kind of geochemical tools, or I should say really like analytical tools that are coming out that are allowing us to learn more about foram geochemistry. And as we'll talk about, a lot of foram geochemistry is the base of our paleoceanographic reconstructions. And so I actually do some work in the modern, studying modern forams, working on developing new paleoproxies, or really working to better understand how their shell chemistry reflects their living environment. So I have one foot in the past and one foot in the present, both of which to try to think about what can we expect in the future.
Super cool. I when I first saw her talk title, I was like, "This is just gonna be something that I'm going to tune out," and I didn't. I feel like the GSW does a lot of that stuff where I'm like, "I'm not gonna be interested in this," and then it's just, "Oh, this is actually really cool." Thank you, GSW. So I think you explained what the oh my god, I'm gonna get this wrong. The PETM is and why it's crucial for studying today, which is really just to say that it's probably our nearest analog towards what is happening today. Is that more or less correct?
Yes, definitely. I can expand on this a little bit, but essentially
Mhm.
during the PTM, we see rapid global warming, we see evidence of ocean acidification, we see changes in the water cycle, and we see a lot of changes in essentially the biogeographic ranges of different critters. We see certain things going extinct, right? So it's definitely a period of abrupt global change that is very similar to what we're starting to see today.
Yeah, and so I wanted to transition, not quite transition, but I wanted to also expand a little bit on a few other terms that you had, which is what the carbon isotope excursion is, and is it exclusive to climate and or oceanography research?
Yes, yeah. One way that we actually recognize the PTM, and to answer your question, both in marine and terrestrial records, is through this distinct change in carbon isotopes. And we see this in pretty much any or many carbon bearing materials during this time. So that could be foram shells, foraminiferal shells, which I had mentioned, right? They're made out of calcium carbonate. So we can actually measure their carbon isotopes and see that we see distinct changes at the onset of this event. But that also includes things like petagenic carbonates. So carbonates that we find in soils. We can also see it in preserved organic matter from this time that has carbon, right? So, pretty much at the PTM, we see this super distinct change towards more negative values. So, we call that a negative carbon isotope excursion or CIE. And we find it all around the world. in all different types of carbon-bearing materials. And it's really this carbon isotope excursion that marks the onset of the event. But also, we can actually use the carbon isotope excursion to do some kind of mass balance calculations and estimate how much carbon was put into the ocean atmosphere system to cause this event. And during the PETM, like I said, if we were going to look at a stratigraphic record across this interval, you see this negative carbon isotope excursion. And it's essentially telling us that there's some sort super, we say isotopically depleted, but essentially very negative carbon entering the ocean atmosphere system. So that could be things like methane could be entering it. If we have burning of organic matter, that could have entered into the ocean atmosphere system to cause the PETM. And bringing it back to thinking about the PETM as a modern analog, as an ancient analog for modern climate change, we're actually seeing the carbon isotope composition of our atmosphere also shift towards negative values right now. And that's essentially because we're taking organic matter or fossil fuels and burning it and adding that to our atmospheric pool. So both during the PTM and today, we're seeing a shift towards negative carbon isotope values that are essentially telling us some sort of carbon is being added to the ocean atmosphere system that's changing the overall pool of carbon. Yeah.
Yeah, it's so interesting. I don't have it in here, but I just can't help thinking, like, what do you say to people today when they just go, this has happened in the past, so it couldn't possibly be anything anthropogenically related?
Yes. Yeah, that's a great question. And I cover this in many of my classes too. We have several forms of evidence how we know that it is like human forcing. And actually, the carbon isotopes is one part of that. So, like I said today, we're seeing that the carbon isotope composition of the atmosphere is becoming more negative. And that's because we're fossil fuels, right? We're adding that CO2 to the atmosphere, and fossil fuels inherently have a very negative carbon isotope signature. So the more we add to the atmosphere, it's drawing down that atmospheric value. However, another major kind of natural CO2 source that we could have is from, say, volcanic emissions, volcanic CO2, right? But if we were actually adding a lot of volcanic CO2 to the atmosphere, we would find our atmospheric carbon isotope value would be becoming more positive over time. So literally the change that we see in carbon isotopes is a huge kind of nail in the coffin showing that this is directly from fossil fuel emissions, right? In terms of why we're having increasing CO2 in the atmosphere. But also, I get a lot of questions, especially about climate change associated with orbital cycles, right? So we have different periods of time where overall Earth is warmer versus cooler because of many different orbital parameters controlling the position of Earth in the solar system, right? And so people are like, oh, it gets warm and cold and there's these cycles. This has happened in the past. Why are we worried about it now? And if you look at records of these kind of warming and cooling, these glacial and interglacial periods over the past several hundred thousands of years, right? What you'll see is that we're going way off of that trajectory. So instead of following this kind of up and down pattern, we just keep going up and up and up and up and up and up. I show a lot of graphs to my students when I'm teaching something like intro oceanography to try to hit this point home that we can see many ways in which we are deviating from our natural background standards.
Neat. Yeah. It's really impactful to talk about this stuff. So thanks.
Yes, no worries.
Yeah. So look, let's chat about forams now. Because I was able to get out of intro to fossils paleontology because I was like, I am a terrible drawer. I don't want to do this. I want to take more geochem classes because I'm a nerd. Anyway, so geochem podcast, let's talk about forams. Your research and the papers that we have here, we talk a lot about foraminifera. So could you talk to us about the role that they play in the geochemical studies of the PETM?
Yeah, definitely. I could give a little Forams 101, right?
Love
So
it.
yeah, they're called foraminifera, but that's too much to say all the time, so we're not going to do that. We say forams, right? Um, and so we have both planktic forams and benthic forams. So benthic forams live either on or in the sediment of the seafloor, right? And then we have planktic forams that live throughout the surface ocean. They mostly live in the upper surface ocean. So either in the mixed layer, which is where we have the surface ocean equilibrating with the atmosphere, or slightly deeper. And so essentially, like I said, these forams, they're composed of calcium carbonate. So as they live their life, say in the surface ocean, they are precipitating a shell. And that shell is essentially geochemically recording the environment in which they live in, right? And over time, we've discovered many different kind of geochemical aspects that we can probe within these forams to learn about all kinds of different conditions. I look a lot both at the stable isotope composition of forams, but also at their trace element geochemistry. In thinking about the PETM, actually, it was first recognized, like this carbon isotope excursion that I'm talking about was first recognized through the study of fossil forams from the Weddell Sea near Antarctica. So essentially, folks didn't even know that there was any type of change in carbon isotopes or a change in the carbon cycling until it was measured in forams in the early 90s. And so, also saying in the early 90s, I feel like it's a relatively recent event, but maybe I'm just lying to myself saying
We're
that the
lying to
early
ourselves.
90s was
We're lying to
relatively,
ourselves.
I guess it is 2025. So I don't know about that
Yeah,
anymore.
it's
But
fine.
yeah, yeah. Okay, so it was early 90s. Yeah, but we can look at their stable carbon isotopes to reconstruct carbon cycling. We can look at their oxygen isotopes to learn things both about temperature and the water cycle. In terms of trace elements, a lot of folks look at magnesium calcium, which is representative or is controlled dominantly by the temperature at which the shell grew. We also have interesting isotope systems like boron isotopes that have been used to reconstruct ocean pH. And all of these things have been measured from forams. And we're continuing to find new chemical tools that we can use to reconstruct other types of conditions like productivity, changes in ocean oxygenation. So so forams have played a super important role in basically shaping our understanding of the PTM, particularly from the oceanic perspective.
I have nothing to say. I love it. It's so interesting. Oh my god. So let's take a step back then. How do you collect these samples?
Yeah,
Are we
that is a
going
good
back on the
question.
boat?
Somebody's going back on that boat. Yeah. So if we're thinking about fossil forams, essentially they come from coring sediments on the seafloor. And a lot of these samples that I have worked with and that many folks in our field have worked with actually come from what was most recently known as the International Ocean Discovery Program, or IODP. But really, IODP is one of many scientific ocean drilling programs that the US has been involved in and actually has spearheaded since the 60s. Like I said, a lot of the cruises I go on are a bit shorter, maybe anywhere from 1 to 3 weeks, whereas on these IODP cruises, they'll have expeditions that have a team of international scientists from several different countries all over the world that go out typically for about 2 months to drill these cores. Yes, I will say, I thought about talking about this for my tea, but I'll say a more serious tea is that the US has recently pulled out of international scientific ocean drilling efforts, which is really disappointing considering the history of scientific ocean drilling in the United States. Even though we have some of our own vessels that we can use for coring in kind of like shelf environments, hopefully in the future, we'll have an opportunity to rejoin the international scientific ocean drilling community and extract even more climate records that can be enlightening to us. Right.
Yeah. No, I appreciate you saying that. So we talked about how we're using isotopes, how we're using geochemistry. Could you just be a little bit more specific about the techniques that we're using to analyze them? What kind of laboratory equipment are we talking about here?
Yes, yeah. This is also a part of my research that I'm really excited about is we're finding more and more we're continually pushing the boundary of the size and scale and scope of the measurements we can make, right? And I said the first paper on the PTM recognizing the carbon isotope excursion for the PTM was in the 90s. And at that time, normally you would take several foraminifera, anywhere from tens to hundreds, and pull them together and put them in a gas source isotope ratio mass spectrometer. So this is something where essentially you would acidify that sample, which would usually with phosphoric acid, and that releases CO2 that can then be pulled into your isotope ratio mass spectrometer to measure the carbon and oxygen isotopes. But actually over time, we've had some really great technological developments that have allowed now to where you can actually measure the carbon isotope values of a single thorium using this same approach, which is really cool. But in addition to doing that gas source isotope ratio mass spectrometry, I also use a lot of in situ techniques for both stable isotopes and trace elements. So some of my work has used SEMS, secondary
Ooh.
ion. Yes, I know. Most people don't think about SEMS and thoriums because,
No.
yeah, it's more of a high temperature geochemistry approach.
Or stick a mineral under it so we can have a look. Yeah.
Yeah,
I love
right.
this. Yeah. Okay.
Yeah. So I've done some work actually analyzing PTM plankton thoriums with SEMS to measure their stable carbon and oxygen isotopes, but on domains that are maybe like 10 microns in size.
Wow.
Yeah.
Ooh.
Yeah. So that has been really helpful for investigating things like diagenesis in forams and how that could alter the interpretations that we're drawing from these records. On the trace element side of things, I use a lot of laser ablation, ICP-MS, inductively coupled plasma mass spectrometry. Say that like 10 times fast.
I can't.
Um,
I'm lazy. I'm like just
yeah,
ICP, ICP-MS.
yeah,
Yeah.
there
Okay.
you go.
Love it.
LANCP-MS.
Yeah.
So I measure trace elements using laser ablation, which
Mm.
also allows for measurements to be made on individual thorium shells. I really like what has been somewhat recently deemed like the individual foraminiferal analysis. So all these different geochemical tools that we have that are allowing us to measure the geochemical signatures of individual thoriums. I could definitely see people being like, why would you ever want to do that?
And we would say as geochemists, why wouldn't you?
Yeah.
Why wouldn't you want to know their selenium content? We don't know. We don't know until we see, and then we know that we don't or we do want to know.
Well, there's just a lot of processes that you can look
Mm.
at if you have populations of data. You can think about things like seasonality, and then a lot that we can learn about diagenesis, about like their life mode and how that might be impacting their geochemistry, and ultimately how all of these things impact our interpretations of ocean climate change at this time. Right.
Totally. Also, not written in your questions, but just thinking if you were to want to go deeper into the geologic record, presumably you couldn't use carbon isotopes, but do you think that the oxygen isotopes would be sufficient?
So I would actually argue the other way around. I would say that the carbon isotopes, because again, these carbon isotopes are locked in carbonates, right? And the carbon isotopes are usually more reliable. The oxygen isotopes have a higher likelihood of diagenetic resetting. But we actually look at carbon and oxygen isotopes in biominerals all the way back to the Cambrian, pretty much.
This is just me not knowing or not being good at isotopes. That's all this is. Because I just was under the impression, and guys, this is why, and I'm not talking to you, I'm talking to the to everybody. This is why you need to ask questions when you don't know something and you shouldn't be ashamed to ask. Just because for me, I was under the impression, but hearing what you're saying about locked isotopes, which we need to talk about, it's just that I thought that after a certain amount of time, carbon isotopes were just gone with the wind.
Oh, I see. You're probably thinking about radiocarbon.
Oh, guys,
So
this is why you ask
this is
questions.
important. Yeah, important distinguish like
Yeah.
difference here. I realize I don't even know if I've said stable this whole time. I'm talking about stable carbon and oxygen isotopes.
Okay.
So 12 to 13, we're not thinking about carbon 14. You're totally right. Yeah. Carbon
Okay.
14 is like,
I'm on board.
yeah, you get past about 56,000 years and there's not
Exactly. And
radio.
that's why I'm like, what are we doing here? Okay, cool.
Yes.
I'm the humble geochemist that always asks about, particularly about isotopes. I've had a few shows where we've done a lot more about isotopes lately. And let me tell you, I've learned more about isotopes these past few shows than I think I've known in my life. Like, I took a really great isotopes course in college, but it just because it was one of those things that it just wasn't my favorite and I just shied away from it. I got through the class, but then I was like, oh, it's a bit much. I don't have room in the brain. But then it comes back and I don't know, I feel like I've learned quite a little bit. Okay, so we can use carbon because we're talking about stable carbon. Cool.
Yes. Yeah. And also I get you do a whole geochemistry podcast. We can only know so much. And I'll tell you, I teach geochemistry, right? So I try to like teach on all these different topics. In reality, we can only have so much depth in so many different things, right? So I get the whole like there is not brain space for this extra information,
I
right?
give a lot of courses in different, obviously mostly geochemistry, but I do spectroscopy as well. And I find I'm always just great question. Let me come back to you on that one. And it's just definitely a better way to go about things as well. But it's just like, where did the depths of knowledge to where this question is trying to probe? Like, where did this person come up with this question? It's a beautiful question. And I feel like I'm just continually surprised by the depths of people's questions. Mine comes out of completely not knowing. I suppose theirs does too. Like nobody's trying to trick you here. It's well, why would you think of that question? Oh, the human mind.
Trust me, I get it. Yesterday, I was lecturing on cosmochemistry, which is about the
Oh,
farthest point from what I do. And I
yeah.
got some really great questions that were followed up with some really in depth Google Scholar searches. So there you go.
Oh my God. I love when, now we're going to just be gossiping everybody. I love when Geological Society of Washington brings in all the NASA people. And I'm just like, the depths of which these people are probing into the universe. It's just, what are you even talking about? This isn't even geoscience anymore. This cosmochemistry. It's incredible.
Pretty
Anyway,
crazy.
it's pretty crazy. Yeah.
Yeah. We pride ourselves as geologists thinking on scales that most people don't. And then you, like you said, you bring in the NASA folks and then you're like, I'm out. No, I'm just kidding.
It's like I'm tracking with you and then you'll say something and then I'm like, we're off track now. They were talking one time about this shuttle, and I forget the name of it now. Guys, I'll try and figure it out and post it somewhere. But it's just this shuttle mission where you have two shuttles that are chasing each other around the world, and they're helping to basically make like LiDAR mapping of the Earth. And I was like, what? How did you guys even think it? Why do they need to chase each other? They explained it, but I've since forgotten. I didn't have space in my brain. Like it's gone. Anyway, guys, let's get back. Now the section I want to chat with is about temperature changes in the oceans. So here I'm really curious as to, we chatted a little bit about the calcium magnesium here, but what other, or even to explain more about them, geochemical proxies have been used to reconstruct temperature changes during the PETM, and what have they revealed?
Yeah, this is a great question. I would say if we are looking in the ocean, probably one of the most common temperature proxies that we use is magnesium calcium in carbonates, right? And so pretty much as carbonates precipitate under higher temperatures, they incorporate more magnesium into the calcite crystal lattice. And so this is something that is not only measured in forams, and just to be super explicit here, like I said at the beginning, we have planktic forams that live in the surface ocean. We have benthic forams that live on the seafloor. And even the ones that live in the surface ocean, they have like different depth habitats that they prefer. So if we can measure, say, magnesium, calcium in forms that live in the surface and maybe ones that live in the thermocline where we transition from like the stable temperatures of the surface to the cooler temperatures of the deep, and even below the thermocline. And then we also measure them on the seafloor. We're essentially looking at part of a water column profile of temperature, right? So we can get pretty detailed into not just, hey, it warmed by this much in the surface ocean here, but we can actually start to think about how temperature was different throughout the water column and what the implications for like circulation, ocean circulation might be. So we do a lot of magnesium, calcium, but there's also organic biomarkers that can be used for temperature reconstruction. So I know there have been some, for example, TEX 86. Now, see, if we go down the organic biomarker field, that's when I start to lose some of those details there. Uh,
Okay.
but I know it exists and I know it happens.
It exists, guys. That's what we need to
Yeah.
know. It
Yeah.
exists.
TEX 86, Google it.
Google it. That's what Google
Um,
Scholars for.
Seriously, though. Yes.
Yeah.
But I think one of the most recent compilations I've seen came out last year, pulling together all these different temperature records. And they essentially found that sea surface temperatures globally changed by about 6 degrees Celsius
Whoa.
at the onset of the PTM, which is crazy,
Yeah.
right? That's a lot.
That's a lot.
Yeah. So, yeah, that's where we're at on the temperature thing. I would say people are still interested in reconstructing temperature wherever they can get a PTM record because we honestly only have so many, right? In the deep sea, there's got to be essentially the stars have to align to get carbonate preservation that is recording the PTM. Because as we have these forms, for example, if we're thinking about planktic forms and they live in the surface ocean, they live, they build their shells, they die, they start to sink to the seafloor. And if the seafloor is below what we call the calcite compensation depth, we're not going to get preservation of that carbonate. So we really only have, in terms of open ocean records, them being preserved on bathymetric highs, like seamounts, for
Oh,
example.
okay.
Yeah. You have to be looking at oceanic crust that existed, the late Paleocene, and that was elevated enough to be above this kind of chemical horizon in the ocean to actually even get these carbonate records preserved. So like I said, the stars have to align. So we try to reconstruct temperature at all of these sites using whatever tools possible.
This is just next level stuff here. How has geochemistry contributed to our understanding of changes in the hydrological cycle during the PETM?
Yeah. So I would say one of the biggest tools that's used here is actually oxygen isotopes.
Mm.
So if we look at oxygen isotopes in carbonates, they're essentially partially controlled by the temperature at which that carbonate was precipitated, as well as the oxygen isotope composition of the water that it grew from. And it turns out that the water signature, the isotope composition of, for example, seawater, can be changed locally, regionally, depending on things like the rate of precipitation versus evaporation, right? So if we have magnesium, if we have temperature that we've reconstructed from magnesium calcium, and then we essentially plug it into an equation where we can back calculate the oxygen isotope composition of the carbonates, of the seawater that the carbonate grew from, then we can look at how that changes through time. And that can tell us something about maybe we're getting more rainfall in certain areas or more evaporation in others. So I'll say one common thing that we have found some evidence of is more precipitation happening near the poles. And we can see this through changes in oxygen isotopes through time.
And it's would that be the modern day poles? I guess it wasn't that long ago.
Yeah,
Yeah.
paleogeography wise, we're like pretty similar-ish.
Oh, that's interesting. Okay.
So it's a little convoluted, but you can do it. Also, I'll say that's from the geochemistry perspective, but a lot of this stuff can be paired with paleontology to
Right.
see if you're seeing like fossil assemblages that like warmer, wetter climates or dry climates.
Sure.
Yeah.
Ugh, okay. Following down this same route, How has then geochem helped in understanding the extent of ocean acidification during the PETM?
Yeah, so this is an interesting question. I would say there's one main proxy that we use to like really try to probe into ocean pH, but we see a lot of sedimentological evidence for ocean acidification during the PETM.
Okay.
One of kind of, I would say, the deep sea poster child sites for looking at ocean acidification are in the wall on the Walvis Ridge, which is a ridge that extends off of the southwest coast of Africa. And so essentially along this ridge, we have a bathymetric transect of PTM records that exist with increasing water depth. And so because of this, we've been able to essentially map out changes in that carbonate compensation depth that I told you about, where the depths below that, we get no carbonate preservation. And so, for example, if there's a lot of CO2 that's put into the atmosphere, it makes its way into the ocean. That depth at which carbonate gets dissolved actually becomes shallower. And so we can see this recorded in kind of the sedimentology that we get along these bathymetric transects. But from a purely geochemical perspective, probably the biggest proxy that's used is boron isotopes. So this is something where under certain pH conditions, you're more likely to get one boron isotope versus the other. And if we pair that with boron calcium ratios, which is a proxy for dissolved inorganic carbon in the ocean, we can reconstruct carbonate chemistry changes. All of that is a lot more complicated than like the 2 sentences I said about it. But if you want like the quick summary, essentially we think that the ocean pH dropped by about 0.3 pH units, which if you hear that, you're like, whatever. What does that mean? But pH is a logarithmic scale. So actually dropping by zero point 0.3 is a lot.
Yeah. Wow.
Not ideal for calcifiers.
Not ideal. Not ideal. So I don't know what this is. Going through more of this, and we chatted quite a bit about diagenesis, but to hit it head on, how does diagenesis impact the interpretation of any of the geochem data from the PETM, and what methods are employed to mitigate these effects?
Yeah, this is a really great question. We're dealing with a low temperature mineral, right? So diagenesis is just very common with carbonates in general. And so I would say one of the biggest issues we have, particularly focusing on PTM records, is like I was just talking about, carbonate chemistry changed a lot during this time. So at the onset of the PTM, we have a lot of dissolution of carbonate records. And then we think that once carbon cycling kind of checks and balances kick in, for example, enhanced terrestrial weathering brings a lot of ions to the ocean, that we likely got almost like a carbonate overshoot, right? So lots of dissolution. And then finally, once we hit a tipping point, our carbon cycle starts working. It's always working, but
Mm.
ramps up. And then we get more weathering, more ions to the ocean. And then we might have gotten actually a lot more carbonate precipitation. And so because we have this kind of fluctuating carbonate chemistry throughout the PTM, we really have to worry about opportunities for, say, recrystallization that could change our geochemical signatures. I mentioned earlier that I had used SIMS, secondary ion mass spectrometry, to measure stable carbon and oxygen isotopes in PTM forams. And the goal of those studies was really to identify, do we have secondary calcite that's growing on these shells that would alter our interpretation if we were to, say, analyze that shell by gas source mass spectrometry, where we just dissolve the whole thing. And I'll say some of my work and also prior work. I think one of the papers that I had sent, Cosden et al., looks at this problem using SIMS and basically identified that we often do have diagenetic overprinting on some of these shells, that unless you're using in situ methods to measure the primary chemistry, you're very likely maybe getting an attenuated signal of environmental change when you include that diagenetic calcite in your kind of whole shell analyses. So it's definitely a problem. I would say there's a lot of research being put into how diagenesis impacts all kinds of different proxies because we've already talked about several different kinds. So there's a lot of work trying to figure out how exactly those can be altered under varying diagenetic regimes.
And something that I've just been thinking about as well, are there differences in the geochem signatures or anything for that matter between terrestrial and marine records from this time period? And really, can we reconcile them or is it still an outstanding question?
Yeah, so this is also a really good question because we actually do have, I would say, one of the biggest problems is with our carbon isotope excursion, right? We talked about how this is what marks that CIE is what marks the onset of the event. But when we actually look at the magnitude, so how much isotopic change we actually get in deep sea or just marine records in general compared to terrestrial records, the terrestrial records tend to record a much larger carbon isotope excursion than the marine records. So there's a lot of questions about why that is. Is it something where the smaller excursion marine records are correct and there's something that is amplifying the signal we see in the terrestrial realm? Or is it the other way around? Maybe diagenesis is really attenuating the extent of this excursion in marine records. And so, with all of this in mind, why does it really matter if terrestrial and marine don't match? Well, with the carbon isotope excursion, that's directly how we model how much carbon had to be put into the system to cause X amount of warming. So, if we're interested in using the PTM as an ancient analog, it's really important that we're able to pin down essentially the extent of that excursion so we can accurately model carbon cycling changes at this time. So that's probably the biggest difference between those two environments, and it is hard to reconcile them, but there's a lot of research being put into that right now, I would say.
Yeah, and following along with that, are there additional challenges to integrate some of these data sets with particularly with the proxy research that's being done and different environments when studying the PETM?
Yeah, I would say yes, definitely. First of all, every different proxy has its own uncertainties, right? That are sometimes straightforward to describe with in terms of putting numbers to it with an error, right? But also is sometimes more difficult, right? So different proxies have different uncertainties that have to do with what we know about the proxy, how those measurements are actually made, what we know about the substrate. So I'll say with forams, a lot of times we're assuming that they're directly recording, say, the signature of the seawater, but sometimes it's not the case, right? And so there's a lot of work that's put into that as well. And then I'm a geochemist, but I also firmly believe it's so important to understand the environment that you're interpreting from, right? Because there's all kinds of different environmental considerations that you have to think about. I do a lot with marine geology. I'm a marine geologist. So even if you're thinking about like a deep sea record versus a coastal plain record, right? There's different considerations that you have to think about in interpreting your geochemical data. And then it gets even crazier if you're trying to compare a marine record data set to a terrestrial one. And I feel like you could have 20 podcast episodes just about areas of uncertainty or difficulties there. But I would say, even with all that being said, the community really does a lot of work to try to be very transparent about uncertainty and also trying to do their best learning what we can from the diversity of records that we have.
Sure. And I think that kind of is true of all geochemistry, right? Like the stuff that I work on, like all that kind of stuff. There's just so many different considerations that you have to take into before you can just say, okay, yeah, drill here. There's just so many different things from analytical methods through to environmental concerns, et cetera, et cetera. Yeah. You are not alone.
Yes.
Okay. And last question that I have in this section is, has geochemical data illuminated anything about the biological responses? So including extinctions and adaptations during this time period?
Yeah, I would say most definitely in many different types of ways. So actually before the carbon isotope excursion was discovered, there was previously identified like a benthic foram extinction that we now know is due to the PETM. But we didn't know that before we had our geochemical record pointing to the environmental changes that coincided with this previously identified like extinction event. So I would say that's a really basic example, but even some of my work has worked to use, say, the geochemistry, specifically stable isotope compositions of individual foram shells to identify sediment reworking and remove that distortion from trying to interpret ecological responses during the PETM. I would say, though I'm 120% biased, right? If you can pair the paleoecology with the geochemistry and vice versa, there's a lot more that you can learn about the system, right? At least in these types of environments. I don't know about deep in the mantle if you have to worry too much about paleoecology to inform your interpretations. But here I'd say it's helpful, definitely.
I love that. And now to switch topics a little bit again, something that I just wanted to revisit super quick was how can these findings from these PETM studies inform strategies to address our modern climate change challenges?
Yeah, this is a really great question. The whole goal of studying these past events is to understand more about the Earth system in general and how it responds to perturbations like this. So I'll say one of the biggest goals of a lot of this research has been to constrain Earth's climate sensitivity. And when we say climate sensitivity, it sounds like a general term, but it's actually a very exact term. We're talking about if we double the amount of atmospheric CO2, how much does that change global temperatures? That's something we're really interested in understanding in the modern. And so the PTM is like a great time to try to understand, again, if we double atmospheric CO2, what temperature do we find? And some more recent studies that have been done on the PTM in similar events, I actually looked this up beforehand because I felt like it was useful to know, have predicted that if we doubled atmospheric CO2, we would see a change of 3.1 to 4.5 degrees Celsius, which is a lot. But that's all from studying the PTM, that they've come up with those numbers, which are actually comparable to other estimates derived from all kinds of other things, right? So I feel like climate sensitivity is a big part of it, but also understanding the timing and rate at which Earth might bounce back from something like this, right? We're really interested if we're perturbing the carbon cycle right now, say we do make efforts to reduce emissions, how long does it take for the Earth to recover naturally? And how does that happen? And how do organisms respond to that? Those are all questions that we really probe through studying deep time analogs like the PTM.
I love that. I think that's just so relevant to what's going on today. And I think it's a really great thing to finish off on, unless you have any other things that you want to share with us,
I feel
or you
like
have many.
I could talk forever. I hope, that if you didn't know about the PTM, now you do. And if you didn't know about forams, now you do. But I feel like we covered a lot of fun things.
Same. So, with that, I want to thank you so much for joining me. And I hope that you enjoyed sharing your research as much as I and we will say enjoyed learning about it. I want to thank our listeners for listening to GeoChemISTea, and a big thanks to Brittany Hupp for dishing some tea and talking to us about climate past and present. Thanks to our sponsor, LKI Consulting, and to It's Water and Coma Media for providing our music. And I'll see everybody next month.